Okay, in this video I will be explaining Hund's rule, the Aufbau principle, and Pauli's exclusion principle. First off, the Aufbau principle. The Aufbau principle is pretty much just a fancy way of stating the element or how many electrons are in the shells. Now, for something like carbon, let me first off say, these are the S section, these are the D sections, and this is the P, and these are the Fs. That'll become more clear what the heck that even means in just a second. So for something like carbon, for the Aufbau principle, you build up from the beginning all this stuff. And note that S over here, this is helium. It's kind of an oddball as it is an S along with all the other P's. So for carbon, you'd start by building up 1s2 because it is the first row for the coefficient. It's an S, and there are two electrons in that row. Now you go down to the next row, 2s2, 2 because it is the second row, S because this is the section it is on the table, and 2 up here because there are 2 in that S section. Now 1s2, 2s2, 2p2. Again, P section and 2 because it's the second in that section. And as you keep going down the table, the Aufbau principle, it gets longer and longer and really more annoying. For something like manganese over here, it is a long one. So you go 1s2. 1 is the coefficient because it is the first row, S because these are both S. Now 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Now it goes 3s, 3p, 4s, 3d, 4p. Why does it dip down to 3d? Well, someone somewhere said that, so we're just going to go with it, and that's just how it works, so get used to it. Now if you go to something like tellurium, it is a pretty tough one. You got to build up a long thing. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and 5p4. It's kind of a big thing, and someone thought of it a way to abbreviate it, and you use the noble gases over here. Just a refresher there: helium, neon, argon, krypton, xenon, and radon. So for this, you look at the elements, say beryllium, and then you look at the noble gas that came before it, in this instance helium. So you would put helium in these brackets and then just start building up like we did in the last page, and yeah, so you just build it up. So helium 2s2. So it doesn't help a whole lot in this scenario, but it does on the bigger stuff. So for something like manganese, you go back, which would be to argon, and then argon bracket 4s2, 3d5. Now if it was chromium, it would be argon bracket 4s2, 3d4, 4 because it is the fourth in that section, and that's the D section, and yeah. Now you try it for something like phosphorus. Okay, phosphorus, you go back, it is neon, that's the noble gas that comes before it. Neon, 3s2, 3p3. 3 because third row, and it is the third in the P section. Okay, now Hund's rule is stating that each shell has orbitals. Orbitals are pairings of electrons. Let's say these little arrow guys are electrons. Now when they fill up, they fill each individual orbital before pairing up with another electron. Notice that? So they fill up each one. So see the S here, that's the Aufbau principle. As we're building up, this is the second row, first row, and so yeah, so you get there, and then it fills each individual orbital before pairing up. Now the Pauli exclusion principle is related to this, but different. So electrons have a spin. Spin is some quantum mechanical function of it, and it is a lot more difficult than I can explain to you, but let's just call it up and down. So as they go, you can't have two up electrons with the same spin. So when they go in, they have opposite spins. See? Opposite, same, 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 opposite, opposite, opposite. That is the Pauli exclusion principle and Hund's rule and the abbreviated version of the Aufbau principle.